Hello, my name is Miss Smith. Today we're going to solve inequalities and graph their solution set on a number line. Our learning target is I can solve inequalities and represent their solution set on a number line. Before we begin, we're going to pause for a moment and turn to page 2 of your glossary and write down the following definitions for inequality and parameter. Inequality, any mathematical sentence that contains the symbol greater than, less than or equal to, or greater than or equal to. Parameter, the independent variable or variables in a system of equations with more than one dependent variable. So if you'll pause the video and resume once you've completed the task of writing down your vocabulary. Now we're going to go through inequalities. An inequality is similar to an equation, but instead of an equal sign, you have an inequality symbol. This is your less than. This is less than or equal to. Greater than or equal to. Some ways you may see this written in words is less than for your less than symbol, is fewer than, is less than or equal to, is no more than, does not exceed, at most. If you have at most $10 to spend, you have $10 or less. Greater than, is no more than, exceeds. Greater than is greater than or equal to, is greater than or equal to, is at least, is no less than. An inequality has an infinite number of solutions. We're going to pause now, and you're going to be asked to write two true inequalities involving integers. Use greater than for one inequality and less than for the second inequality. If you'll pause the video, complete the activities on page 20 and 21, and then resume the video. Now, I did the same task that you just completed. Inequality number 1 is true. 10 is greater than 8. Inequality number 2 is true. Negative 20 is less than 8. I added, subtracted, multiplied, and divided the true inequality by 2. And when I add 2 to both sides, it remained true. When I subtracted 2 from both sides, it remained true. When I multiplied both sides by 2, it remained true. When I divided both sides by 2, it remained true. So in this one, if I add, subtract, multiply, or divide by 2, all the inequalities remain true. Inequality number 2, I did the same thing. Negative 20 is less than 8. I add 2 to both sides. Negative 18 is less than 10. That remained true. I subtracted 2 from both sides. Negative 20 is less than 6, remains true. I multiplied both sides by 2. Negative 40 is less than 16, remains true. I divided both sides by 2, and negative 10 is less than 4 is true. So on both of my inequalities, when I add, subtract, multiply, or divide by a positive, the statements remain true. Then I took my same inequalities, and instead of using 2, I used negative 2. So my first inequality I started with was 10 was greater than 8. I add negative 2 to both sides. 8 is still greater than 6, true. I subtract negative 2 from both sides, and that with 12 is greater than 10, still true. But I want you to notice what happened whenever I multiplied by negative 2. I get negative 20 is greater than negative 16. That's false. So to make that statement true, I must reverse that inequality symbol. I did the same thing with division. I divided by negative 2. I started out with a true statement. 10 is greater than 8. But when I divide by negative 2, negative 5 is not greater than negative 4. It becomes a false statement. So to make it a true statement, I have to reverse the inequality symbol. So notice, adding or subtracting by negative 2 did not change the truth of the inequality. However, multiplying or dividing by a negative 2 made the inequality false. The inequality symbol had to be reversed to make the inequality true. Now I want to look at my second inequality and see if the same thing happens. So on my second inequality, negative 20 is less than 8. That's true. I add a negative 2 to both sides. I get negative 2. Negative 22 is less than 6. Still true. I subtract negative 2 from both sides. I get negative 18 is less than 10. That's true as well. But notice again, when I multiplied and divided by negative 2, my statements turn out to be false. 40 is not less than negative 16. 40 is greater than negative 16. So to make the statement true, I had to reverse that inequality symbol. When I divided by the negative 2, started off with a true statement, but when I divide by the negative 2, I get 10 is less than negative 4. That's false. 10 is greater than negative 4. If you multiply or divide an inequality by a negative number, you must reverse the inequality symbol. So from this activity, it leads us to the conclusion that when we multiply or divide by a negative, we must switch the direction of the sign. Otherwise, all strategies we use when solving inequalities remain the same. Since inequalities have an infinite number of solutions, we typically show the solutions to an inequality on a number line. Below is an example of an equation, which has an equal sign, and an inequality, which contains an inequality symbol. When I solve the equation, I get x equals 3, so I'll go to 3 and I put a solid point, meaning 3 is the solution to that equation. If I plug 3 in, 3 plus 2 equals 5, it makes it true. Now over here, I subtract 2 by using inverse operations to solve my inequality. X is less than or equal to 3. So I go to 3. 3 will make this true. 3 plus 2 is less than or equal to 5. 5 is less than or equal to 5. It's equal to 5. So it's true. So 3 works, but all the numbers to the left also work. If you plug 0 in, 0 plus 2 is less than or equal to 5. 2 is less than or equal to 5. Everything on that side is true. I do want to remind you about when you graph the solution set of an inequality. I wrote a few down. You have to first decide whether the circle is opened or closed. If the number is part of the solution set, it's closed. If it's not part of the solution set, it's open. X is greater than or equal to 4. So I go to 4. 4 makes that true. 4 is equal to 4. So it's a closed circle because it's part of the solution set because of the equal to. And greater is to the right. So I shade to the right. All the numbers on the right are part of the solution set as well as 4. X is less than negative 7. It's an open circle because if I put negative 7 in there, negative 7 will not make that true. It's not part of the solution set, it's just part of the boundary. And less is to the left. So all numbers to the left of negative 7 work, but the numbers to the right do not. X is less than or equal to 4. So it's a closed circle because of the equal to. 4 does work. 4 is equal to 4. And less to the left. Now make sure you put an arrow because it keeps going even though we stop drawing our number line. X is greater than negative 2. It's an open circle and it goes to the right. Now if your variable is not on the left-hand side, you need to reverse your inequality symbol because what you're graphing is the solutions for the variable. If 2 is less than x, that means x has to be greater than 2. See, this says 2 is less than x. Therefore, x is greater than 2, so it's an open circle, and it goes to the right because greater are numbers on the right side of the number line. I'm going to switch this one around. If negative 4 is greater than x, x is less than negative 4. It's an open circle, and it goes to the left. Now we're going to take some time and solve a few problems and graph their solution set on a number line. When you're solving an inequality, it's very much like solving an equation, except for if you multiply or divide by a negative number, you must reverse your inequality symbol. And you use inverse operations to isolate the variable. So I want to get x by itself, so first I'm going to get 3x by itself. The inverse of subtracting 2 is adding 2. 3x is less than 12. Remember to bring your inequality symbol down. What it does, multiplication, division, so divide both sides by 3. I divide by a positive, so I leave my inequality symbol as it is. X is less than 4, so it's an open circle, and it's to the left. The next problem, use the distributive property to get rid of the parentheses. 3 times 2x, 6x, 3 times -1, -3. And now I want to get x by itself, but first I'm going to get 6x by itself, so I add 3. Using inverse operations, bring down my inequality symbol, divide by 6. Now again, I divided by a positive number, so I don't switch my inequality symbol. I just bring it down the way it is. But if I multiply or divide by a negative, I do have to switch it. So x is greater than or equal to 2. So if I go to the number line, 2 is part of the solution set, and greater is to the right. This next problem, you do the same way. I want to get c by itself. Well, c is on the right-hand side. I'm going to go ahead and divide by -2. But when I divide by negative, that inequality symbol must switch. I circle it to tell myself in the next step to flip it around. So I change it from less to greater. But when I graph this one, I want my variable on the left. -2 is greater than c, so c is less than -2. So on a number line, you're going to go to -2, put an open circle, and less is to the left. If you will now pause the video and do examples 1, 2, and 3, and then press resume when you'd like to see them explained. Now that you've had time to work out 3 examples, we're going to go over those 3 examples. We're wanting to get 2x by itself, so undoing adding by subtracting. So I get 2x is less than 4. I undo multiplying by dividing. Notice I'm keeping my inequality symbol. I divide by positive. I don't do anything to the inequality symbol. X is less than 2. So it's an open circle because it's not equal to. And you shade to the left. Now notice I need to bold that side out. 2 won't work, but every number on the left will. Example number 2. I add 4. I get -3x is greater than or equal to 15. Now notice I'm about to divide by -3. When I divide by negative, I'm going to have to switch that inequality symbol. So x is less than or equal to -5. Don't forget, if you multiply or divide by negative, to switch that inequality symbol. Notice, add 4 to both sides, I didn't change it. But when I divide by that negative, I do. So it's a closed circle at -5, because -5 will work because of the equal to, and less is to the left. On example 3, you divide by -3. Now again, I divided by a negative, so that inequality symbol has to switch. So I end up getting -6 is greater than c. But when I graph this, I want my variable on the left-hand side, so I'm going to flip it all around. I'm going to switch it so that my variable's on the left. If -6 is greater than c, that means that c is less than -6. So it's an open circle at -6. And to the left. So in conclusion, solving an inequality is very much like solving an equation, except for if you multiply or divide by a negative number, you must switch the inequality symbol. Below is a table that may be helpful to you. If the variable's on the left-hand side, you can use this as a guide, but the variable has to be on the left. If it's less than, it's an open circle, meaning the number's not part of the solution set, and you shade to the left. If it's greater than, it's open circle, which means the number's not part of the solution set, and you shade to the right. If it's less than or equal to, it's a closed circle, the number is part of the solution set. Less, the numbers on the left are less. Greater than or equal to is a closed circle, and you shade to the right. So your learning target is, I can solve inequalities and graph their solution set on a number line. If you will complete the activity practice problems on page 23 at this time. If you have any questions about this video, please ask your teacher.